Thank you once again for inviting me to give a short talk during this workshop. As Ulysses mentioned, I'm a member of the Sci Machine Learning Lab, and I've been very excited about the workshops that have been given, the outreach, and the methodologies that have been developed. So today, what I'd like to do is just give you a brief introduction to high-performance research computing at Texas A&M University for those who are not so familiar with our resources. And then some of the very interesting and novel upcoming hardware that we will have that should be very good at allowing you to perform calculations in scientific machine learning that otherwise would not be available or capable, possible. There we go. Okay, so what is high performance research computing? So our mission is to enable research discoveries that advance science and technology. Okay, we definitely want to enable computational and data enabled research activities for students, faculty, and staff at Texas A&M University and at the national level. Okay. Not only do we provide hardware, but we provide consulting, technical documentation, training, and support of these resources. So there's a lot of services that we provide. Number one is that we provide a lot of hardware for your computing needs. We have clusters that provide over 7.98 petaflops of total computing capacity, over 18.3 petabytes of raw storage for active users. We have 4 clusters named Grace, Vital, Terra, and Faster, and I will be discussing our upcoming cluster that will be named ACES. If you would like more information and comparison of these clusters, you can visit the link right there, and it will give you a nice synopsis, the comparison of the hardware available for those. Right? We have 16 professionals on staff and 10 student workers, because not only is it important to provide the hardware for your computing needs, but assistance in utilizing that hardware. And that's where the professionals and the student workers become essential. Access is open and free of charge to all faculty and research staff, students, and external collaborators. Okay, you do need to apply for an account on the system. We do have support available to getting you started and working through the application process. Application process is not difficult, just sometimes it can be a little bit confusing for new users, so we provide that support. We have individual consulting and help desk user services. We also have advanced support for sponsored research projects. And we've started a liaison program under the HPRC Enablement Division, which I am the Associate Director for. We have enablement staff from the College of Science, Health Science Center, and the College of Geosciences. We have expertise in many science and engineering research domains, okay, to help you with your computational projects. And we have lots of training classes and workshops for novices and experts. Okay, so I'd like to go through just a little bit about our more traditional hardware, and then we'll move into the less traditional hardware. So Terra is our oldest system right now that we have online. It has 8,500 core, and it has some accelerators on it, NVIDIA K80s and NVIDIA V100s. And of course, we always have a very fast interconnect between the compute nodes so that you can scale up your computational projects. I'd like to mention Vital. I know there's a lot of information on this slide, but if you have a need for secure and compliant systems, so if you have data that is restricted, such as HIPAA data or other restricted data, then you can inquire on using our secure and compliant system, Vital. The system has 24 compute nodes and also has some accelerators, and it is unique in that it can support both Windows and Linux environments. It's our only system that supports Windows, and we do have 2 petabytes of storage available on that system. And it's housed in the West Campus data center, which is a highly secure data center. Grace is our flagship system. It's a very large system, lots of compute nodes. We have 800 compute nodes that have 24 core Intel processors. So we have a total of 48 core per node and 384 gigabytes of memory per node. We have 100 nodes that have 2 NVIDIA A100s per node. okay, for your computing needs that need an accelerator. And then we have 8 nodes that have 4 T4 single precision GPUs, and 9 GPU nodes that have 2 RTX 6000s, if you are interested in using the RTX 6000s. If you also have very large memory needs, we have 8 large memory compute nodes that have 3 terabytes of memory on them. And we have a little over 5 petabytes of usable parallel file system. Okay, so that is our traditional offering in HPC. So let's talk about the upcoming modern HPC that we're going to be providing. So the legacy HPC is built on, converged hardware. You get a static design, it's delivered, it's static, you can't change it pretty much once you've ordered it and you put it in place. So you have to decide what to purchase ahead of time and try to determine what the future needs are going to be, so that you can order that static hardware and hope that it will handle upcoming new methodologies in the 3 to 5 years that you have the system online. Okay, so it has fixed GPUs, accelerators, fixed memory, fixed motherboards, fixed CPU, everything. All right, and legacy storage with SATA and SAS. In the future, the modern HPC will not have fixed configurations. Okay, it'll be built on disaggregated hardware. You'll have a composable hardware platform. You'll have composable GPUs, accelerators, memory, okay, and modern storage. So this is a diagram that just kind of illustrates what you can have with this modern HPC architecture. You can have this, command center that handles disaggregated pools of resources. That can be pools of GPUs, pools of other accelerators, pools of memory, okay, pools of networking devices. It can have pools of all sorts of things. And what it does is it will aggregate them based on your request, okay, and tie them to the motherboard. So that would be making, your designation of what server 1 should look like, what you need for server 2, okay? So instead of having the static hardware, you get to dynamically allocate it. And that's what the future is in modern HPC. So what we have deployed and is very, very close to being available to our users is FASTER, Fostering Accelerated Scientific Transformations, Education and Research. Okay, so this is an MRI funded grant, and it has Ice Lake CPUs in it, very fast interconnect, and a pool of GPUs. We have A100s, A10s, A30s, A40s, and T4s. Okay, and these are going to be distributed in these pools of resources. And what you can do is say, okay, I need up to 20 of these different types of accelerators, and it will assign them to a compute node. Okay, and in the future, this may go higher. Right now, we're at about 20 GPUs where we can assign those or aggregate them to a compute node. So what this means for you is, let's say you have your scientific machine learning or your machine learning procedure, your algorithm, your processes, and it scales well for GPUs that are on a single compute node. So historically, you would go and you would buy a machine learning box, and the machine learning box would have a motherboard with maybe 16 GPUs on it. Okay, and that's a single box with 16 GPUs. And if you don't use all 16 GPUs, then the other ones are wasted while you're running your 1 GPU job. And then you can scale up to 16, but it's all on one compute node and it's a static structure. With the composable technology, you get to grab what you need. So if you want to use up to 20 GPUs, you can put them on the compute node. They're not distributed across compute nodes, so your programming is much simpler. Okay, trying to program in machine learning where you have the GPUs on a single compute node is much simpler than trying to do the distributed across compute nodes. And then when you're done with it, you just release the GPUs for other people to use. So if you only need 2 GPUs, you say, I want 2 GPUs. If you want 4, then you grab 4. And that's the beauty of the disaggregated resources, the pool of resources, that you can just grab what you need. And so you have the flexibility and you get to compose what the compute node looks like. Okay, so this is what I wanted to focus on today, and what I wanted to introduce you to is we just got a grant from NSF for ACES, Accelerating Computing for Emerging Sciences. Okay, and what this new system will have is many novel types of accelerators. So FASTER is novel in the fact that it has the composable architecture, okay, where you get to compose your compute nodes from the disaggregated resources. ACES goes one step further and not only has the composable architecture, but it also introduces novel, innovative accelerators. Okay, so a large number of novel accelerators to design new machine learning and other algorithms on these accelerators that go past your standard GPUs. Oh, sorry. One thing I forgot to mention is this is being developed with Texas A&M University and partnering with TAC and University of Illinois at Champaign. Okay, so a little bit about the system. The allocated resources that we will have available is a total of 11,000 core. For the CPU-centric computing with variable memory, it's 120 total nodes with 11,000 core. This will have the Intel Sapphire Rapids CPUs. Okay, so they'll be very novel CPUs with high bandwidth memory access. So 96 cores per node. So we have a lot of cores with shared memory and 512 gigabytes of shared memory. We will also have 1.6 terabytes of local NVMe storage, along with the global NVIDIA Mellanox 400 gigabyte InfiniBand accessible storage. It will also have the liquid composable infrastructure, so you can dynamically allocate what you need. Right now, like I said, it was up to 20 of the different accelerators that you're interested in or whatever is available. And we will also have fast transfer or data transfer nodes. We'll have 2 of those on a 100 gigabit network if you need to transfer large amounts of data. So the accelerators that we will be including, graph core IPUs. We'll be including FPGAs from Intel. These would be the next generation Intel FPGAs, next silicon coprocessors, NEC vector engines, the Intel Ponte Vecchio GPU, that will be the first of its kind, and the liquid Intel Optane PCIe SSDs. Okay. So all of these will be dynamically allocatable. So the challenge and the exciting part of this is porting your machine learning algorithms to these new accelerators. So we will be providing support and guidance on porting your workloads to these new accelerators. So this is a very exciting system that will be the first of its kind. So we will be having a kickoff meeting for this project this afternoon, and I would encourage everybody to join us. I will also put this Zoom link in the chat, and it should be posted on our webpage. So we have the kickoff meeting where you can learn a lot more about the project and the timelines, milestones, and how you can get involved in it. Okay, so it's this afternoon at 2 p.m. Central Time, and I hope that everyone will be able to join us. Okay, so I wanted to mention just some of the other resources that we have. We provide training, and this is just a synopsis of some of the training courses that we provide. Primers to get you started. This Friday, we have a technology lab. So if you're new to machine learning, or if you're new to HPC and HPRC, using AI frameworks and Jupyter Notebook using our portal, I would encourage you to take a look at that and sign up for that. We do record these, but it really is good if you could attend during the time. There's a lot of hands-on for the technology lab. And so the biggest benefit that you'll get is if you attend. during the time of the short course. Okay. We also have, Python, scientific Python, and the list is quite long. So please visit our training page and see our short courses, upcoming short courses, past courses. Okay, so this is just the Friday, and I'll go ahead and skip that interest of time. We also have YouTube videos, training videos, and we bring more and more new ones up regularly. So you see these were just posted a few days ago. These were our primers from the fall. So we add new training videos regularly. Getting started. If you're just getting started with HPRC, I would encourage you to go to the playlist for the Getting Started on HPRC. They're like 5-minute videos that really is a synopsis of applying for accounts, getting on the systems, the portal. So lots of good training videos and extensive videos. We provide a lot of pre-installed software that you can access via modules. This makes it very easy to get started with whatever software you're interested in. So you can visit this page and it will show you. And if you can't find what you're looking for, please reach out to us and we can either show you how to install it or we can install it for you depending on what it is. We have an advanced support program. The advanced support program, we can assist in your software, porting the application to our clusters, most definitely, optimizing your code and so forth. We also have the series of our own Bring Your Own. So we have a Bring Your Own code that we've started up again, Bring Your Own molecule, Bring Your Own genome. So you can visit the advanced support program page to find out more information about that. Okay, the portal allows you to run things like Jupyter Notebook through your web browser. Okay, so you can access the HPC systems through the portal and run graphical programs, run Jupyter Notebooks. We have a long list of software that we support through the portal. I'm sorry, I forgot to update this one. Ada was our last machine. You'll notice it's not here anymore. So Terra Portal, Grace Portal with new software. Okay, so this is just illustrating you can run ParaView with graphical. Through your web browser, you don't have to install anything. It's highly responsive, you can rotate. So it's a wonderful way of accessing our resources. And we also have a toolbox which helps you through the portal see what you have available to you, what your quota is, how many SUs you have, and cluster statistics. So if you're interested in learning more, always you can reach out to us at help@hprc.tampa.edu. Please go to our webpage, visit our YouTube channel. And if you want to apply for an account, just go to the quick links and apply for an account. Okay.
Thank you, Lisa. This is outstanding. Look, I should goes without saying that this is a crucial component of scientific machine learning efforts here, because to train these deep neural network models, you really need fast machines. We cannot do much without strong high performance computing support. And so I encourage everyone to, use these resources and reach out to Lisa and John and others if you have questions. So any questions right now from the audience?
I have a question.
Yes.
Hey, Lisa, very impressive. It seems to me that user engagement just keeps improving, year after year, in a dramatic way. I'm so excited. I wish I had time to do my coding on my own. I don't have time because I'm PI and my students and postdocs are doing all the fun stuff. Yes. But I so much wish to have the time to play with, HPRC now. It looks just so much fun. I have a question about ACES. Is ACES going to be part of EXCEED or whatever is the next generation NSF network of resources?
Yes.
So to access
ACES is part of EXCEED. Yes, that is correct. So is FASTER, actually.
I know. So basically to access ACES, you know, A&M PIs are the same as any PI anywhere in the US that has access to NSF resources, correct? So there's no, so that's the way to go. So we have to go to, you know,
You do not have to go through Exceed.
Okay.
No, because we only, a certain percentage of it is available through Exceed. But as an A&M faculty, you get direct access through us.
What is the
You can
distribution?
also,
What
you
is
can
the
also go
partition?
through Exceed. That will be covered in the afternoon session, I believe.
Okay. I don't know if I can attend because I have a lot of things to do, but I will try. And if not, I'll check the recorded, you know,
I
session.
will,
But
and I'll double check the slides. And if it's not listed on the slides, I'll see about getting it added to it.
But
And
anyways,
if not,
you know,
I'll follow up with you.
this is outstanding. And just so everybody knows, I mean, you know, for an HPRC facility to get two large, you know, NSF MRIs almost back to back, right? You know, probably a year or 2 years, you know, apart or something like that. Maybe a year
Oh,
apart.
the
I don't
second
know.
one's not an MRI. The second one is ACES.
Yes, sorry, MRI
that's
or,
okay.
or a bigger, sorry, my bad, but MRI and then another NSF like cyber program, you know, almost back to back is really outstanding. So
Yes,
excellent
we've
job.
had very, very good leadership with Hangao. Hangao, the
Yes,
director
I
of HPRC,
totally
done a
agree.
wonderful job. Yes. I did want to mention, thank you, Ray. Did I answer all your questions?
Yes.
Okay. I did want to mention that, you know, I mean, if you're running your machine learning on your laptop, your desktop, and you're sitting around waiting for it to finish before you can run the next one, you want to move on to the HPC systems. Okay. There's definitely a learning curve. I won't lie to you. There's a little bit of a learning curve, but it's worth it. It's definitely worth it. And we're here to help you with it. So I would strongly encourage you to get started sooner than later, because when you need it, and you won't be able to figure it out at that time. So get started now, and then and encourage your students to get started now and get familiar with it so that it's available to them when they need it. Okay.
Thank you, Lisa. Look, one of the questions I have is the slide you skipped. Actually, I think it's about the training session on Friday.
On Friday, yes.
For the notebook, the Jupyter notebook. And this, I think, is one of the greatest things, is that in the past, you had to go command line, you know, submit a job and do all that, you know, command line stuff. Now you have this ability to use, just like Google Colab, basically, right? I mean, it works like Google
similar.
It works like Google Colab. So essentially, I think this will be very important to make this accessible. And so I actually,
if I may say something, I mean, this is like, if we consider this setup like this could be significantly, you know, impactful in any classes that we teach on machine, like, you know,
exactly
any level of machine learning, right? Because you could have these Google Colabs or equivalent. You can share them with the students. You can have the students collaborate with each other, and you have direct access to these very powerful computing systems, right?
Right. So, absolutely. This is great to make it more accessible.
The only thing that we ask is we support many university courses. We have a very long list of university courses that we support. Please communicate with us if you will be using our systems for courses, so that we can ensure that the resources are available when you have class. Okay, and that we don't have a conflict with our maintenance schedule and so forth. So just communicate with us, and we will make sure that things are available for your course.
This is a good hook to say that we are going to be teaching a new scientific machine learning class in the spring for the students and even professors attending. So we are teaching this, and we hope to count on your support, Lisa, and the HPC to teach this class. So, all right. Any more questions from the audience?